And this time we're talking about parametric equations. So I'm sure the first thing on your mind is, what is a parametric equation? Well, it's where you define an equation or a function like this. Rather than saying y equals a function of x, you say that y is a function. Try that again. You define the y value as a function of some other variable t, and x as a different function of some variable t. And these two, so the value of t defines the shape of the curve, and then the coordinate on the y coordinate of that point on the curve, given by some singular t value, this function tells you what that x value is, and this function will tell you what this y value is. So it's kind of like a middle ground, sort of middleman situation where, maybe you don't know, or it's not possible to sort of put this together in sort of y in terms of x, but you can define a function, in terms of this. You have this sort of variable t, and you can map it onto the y and x axis with these functions. And sometimes it might be that t is actually a thing, and processing it into x and y values. So maybe t is time, and it doesn't have to be time. I just picked it because t is usually time, but it could be anything. And then the value of x, whatever that might be a function of time, and the value of y might be a function of time. So it might be concentration of a particular chemical in solution, and it might be the heat that's produced, and maybe both of those are a function of time and related in this sort of parametric way, where the one graph is drawn as these two separate relationships between the middle thing t and the x and the y axis. So I've got 4 examples, because it's probably easier just to go through some examples and sort of see it in action, and then if there's anything I don't cover that you come across, you can always pop something in the comments and I can try and explain what's going on there for you. So we have a curve, and it has parametric equations where the x term is natural log of t plus 3, and y is 1 over t plus 5, and it is specified that t is greater than minus 2. Now what you can do is you can turn 2 separate parametric equations into a Cartesian equation, so y is a function of x, and where x has to be greater than a certain value. That's because of the limitation of t, and we need to find that out as well. Okay, well, it's very straightforward to do this. I say it's very straightforward to do. What you can do is you can reorder one of them to be t equals. So if we could change this one, for example, into t equals a function of y, then we could just substitute that in and pop it in there and rearrange it until we get y equals. However, with this log here, I'm thinking actually, although that's not as bad to rearrange this thing, I think it might be easier to get this t in terms of x. We'll get an exponential and things like that. Anyway, let's give it a go. It shouldn't matter which way we do it, it's just which is going to be easier to rearrange later. So let's start with this chap. X equals log of t plus 3. And so to get rid of the logs, we're going to go e to the power of x is e to the power of log blah blah, and the e and the log cancel. So e to the power of x is t plus 3. And then we can just rearrange this by getting rid of the 3, and we can say that t equals e to the x minus 3. So that's quite nice, quite straightforward. And now we can just substitute that into the y equals, and we get y equals 1 over e to the x minus 3 instead of the t plus 5. Well, of course, we're not going to leave it like that. We can simplify the 5 and the minus 3 to give plus 2. So this is quite nice now. We have it in a nice little formula. Y is a function of x, but we do have this situation where we've got to say x has to be greater than k. Now, if we want to find the domain and range of this thing, which is kind of what we want. Here we want the domain. We want what values can we put in as x. But also, in the next part, I can see we want to find the range of this thing. So actually, the domain of f of x is the same as the range of this thing, okay, of I'll say what we're going to say, we need to say the function of t, but of the x coordinate. So let's say the x function of t. So it's the range of this thing. And the range of f of x is going to be the range of the y function of t. Okay, so if we look at what those are, we can get the domain and the range of this. Now, you could look at this and say, oh, well, what numbers could we put in, all this kind of stuff, but I think you will miss a trick there, because there is a limit to what the domain and ranges are here, because they have limited down the t. So I think we're going to stick with looking at it in this respect. So we want to find the domain of this, so what values x can be. So we need to look at the range of this thing. The smallest value of t we can use is -2. Well, okay, we can't use it, but that's the limit, isn't it? And so if we put that into here, it should give us the smallest amount of x, which should then give us the range. If that's the smallest amount, we can be anything above it. So log of -2 plus 3 is log of 1, and log of 1 is 0. So the domain of this is that x has to be greater than 0. We're not allowed to be equal to 0 because it wasn't allowed to be equal to -2 up here. Write down the range of f of x. Well, the range of f of x is the range of the y function of t. So it's the range of this. So again, we can look at the smallest value we can get, which is t is -2, and we can put that in and see what we get. If y equals 1 over -2 plus 5, so that's 3, so y equals a third. Okay, if we put in bigger numbers, well, actually, this isn't the minimum at all, is it? So we've put a bigger number in, then this is actually going to get smaller. If we put in 10, positive 10, then that's going to be 1 over 15, which is a smaller number. Put in 100, 1 over 105, which is a lot smaller. If we put in a ridiculously large number, as this goes to infinity, in fact, then this becomes 1 over infinity. Now, you can't sort of put infinity to algebra, we're just sort of thinking on page. So 1 over basically infinity plus 5. Well, 5 is so small that it's basically just saying it's infinity. And, you know, what number is going to be created when you do 1 divided by infinity? Well, it kind of makes no sense. It's tending to 0, essentially. If you have 1 divided by a ridiculously large number, then that is going to get smaller and smaller and smaller, closer and closer to 0. And if you think about it, we can see that if we draw a graph of that, of y against t, then we know that apart from the plus 5, which is going to shift the whole thing in the x-axis, because we've added onto the 5 beforehand, 1 over t is a reciprocal like this. And so plussing the 5 is going to shift it across and make it come over like this. But it's still, as you, if you're looking for the range of y values, that is limiting, it's cutting the top off there at a third, and then this is getting closer and closer and closer and closer and closer to 0 on the y-axis, but never reaching it, because it's divided by a bigger number and it's getting smaller. So what we can say is that therefore y will be less than a third, because that's our biggest value, but we can't be it because we couldn't be equal to that, and greater than 0. And again, as long as we put it as a strict inequality rather than saying equals, then that's absolutely fine to say that. It'll never reach 0, but it will be greater than 0, even if it's just a tiny, tiny, tiny amount. So that's our range, and we've got our domain, and we've got our Cartesian equation. Have a look at another example. And here we've got a curve C with parametric equations, lovely, x and y, show that the Cartesian equation of C can be written in the form of some bracket and some other bracket squared and equaling x squared. Okay. So again, we need to think how we can do this. We could rearrange one and substitute it in the other, like we did before. This has got t in two places, but then I don't know, because we've got interesting things going on here. Let's just try different things. First of all, let's look at this one. It's only got t once, so we might be able to do something with that. We could say that t squared equals 4 minus y. Now, unfortunately, we can't just substitute that straight in, because if we did, we've got t squared, not t, so it would be a bit weird. We'd get something like x equals 4 minus y times the square root of 4 minus y minus the square root of 4 minus y. Not convinced about that. Maybe it's something that we could, well, maybe, because if we square that, we'd have to square all of this. We might find that these roots cancel out. Maybe it's worth persevering with this for a little bit. So this squared would be 4 minus y times 4 minus y times this thing, which is going to be, times this thing squared. Because we're squaring the whole thing, so it's that squared times that squared, which just gives us another 4 minus y, or 4 minus y cubed. And then we've got minus, well, we've got to do two lots of these two things times together. Well, this times this is going to give us 4 minus y, times this is going to give us 4 minus y squared, and then we are going to need two of those. And finally, we're going to add this times this, which is 4 minus y, which we'll just put in the bracket for the sake of that. Okay, so how are we going to get this into this form? Well, it feels like we're not far off, but we're not there yet. We have got a 4 minus y everywhere, but if I just factorize that out, we're not going to get into a form unless we can then unless what's left can be factorized again. So okay, let's try that. We'll delete this, give us a bit of space. Because everything's got a 4 minus y in it, we can say, okay, it's 4 minus y times, well, let's do a square bracket just so we can see where we are. Square bracket, 4 minus y squared minus 2 times 4 minus y plus 1. And now, can we factorize this into a bracket squared? Maybe. If this was u instead, if it was u squared minus 2u plus 1, what would that factorize to? It would factorize to a u times a u, 1 times a 1, and both of them minus, wouldn't it? Because that would then expand to u squared minus u is minus 2u, and minus 1 times minus 1 is plus 1. That's supposed to be a 1. Made it even worse now. So we can factorize this. So get rid of this line. Obviously, you'll be working down your page. You won't have to keep deleting things. We've now got 4 minus y, and then this thing is going to change into u minus 1, which is 4 minus y. Remember, that's what u is, but with an extra minus 1. So it's 3 minus y times 3 minus y, or indeed 3 minus y squared. So, and that's exactly what we've now been asked for. This was x squared up here because we squared it, if you remember back when we did the substitution. And we've got it in this form, and we know that a is 4 and b is 3. In part B, it asks to write down the maximum value of the y-coordinate for any point on this curve. Now, you might be tempted to look at this thing and go, oh, how are we going to maximize the y value? Not a good place to look, okay? So don't be tempted to do this. The fact it says write down suggests it should be something really straightforward to just look at. And you can do it in the parametrics because remember, t is just a different variable. So whatever values we put into t, the maximum y value we can get can be from this function of t. T can be any real number. So it's just a case of looking at what number can we put in to give this as a maximum. And the fact that we're taking it away, t squared is always going to be a positive number. So if that's a positive number, then it doesn't matter. We're not going to get minus anything like that. The biggest value of y we're going to get is when this becomes 0, so that we're taking the least amount. So the maximum value of y, or y max, equals 4. And we can just take it straight from the parametrics. So do watch out for that phrase write down, because it's a little clue not to go diving into some off tangent. I'm going to stop this video here because it's getting quite long. I'm going to do another one on exactly the same thing, but involving some trig functions. But I think rather than having a half-hour video, I'll split the two videos here. So if you've got any questions or comments on these two examples that I've done, then pop them down below, and if it warrants it, I can always do another video to explain things. Okay, cheerio for now.